There's a lot of interest in drone acoustics, both from the point of view of community noise and also using sound to detect drones. If this test goes as expected, I'll be able to make acoustic images of the drone flying around, and if it lands successfully, I'll be able to use it in subsequent outdoor tests. This video illustrates the use of BeamformX to process a recorded binary file. We start BeamformX, we see the operating mode dialog, and then we choose the file. At this point, BeamformX is reading the data from the file and processing it as if it were a file from a connected array. The drone will take off and we'll see it fly around. While that's happening, we can see the spectrum changing over time. We can also see the spectrogram updating over time. The spectrogram shows the sound pressure level as a function of time and frequency. Let's pause the input and go back to the spectrogram, and we see that we can click on interesting features and it automatically tunes the display to show the time and the frequency that was clicked on. There's an interesting line at 16 kilohertz. If we click on that, we'll see what it looks like. We can improve the detail by setting the time near the beginning of the flight where the drone was lower, and then further adjusting the time using the time slider to find the best image that we can. So we're going down. Oops, that was too far. Let's go back up. So the height was about 1/2 meter at this point, so we set it at 1/2 meter. This is what the image looks like at 16 kilohertz. To see it at other frequencies, we'll do a frequency sweep. So we turn on record beamforming to save the beamformed images and do a frequency sweep going from 3 kilohertz to 20 kilohertz and do OK. Now we see the image at each frequency being computed. It's also stored in the stack in the back. This is the spectrum that shows the array median sound pressure level and as well as the beamforming peak sound pressure level for each frequency. Looking at the recorded stack, we see the last frequency of 20 kilohertz. If we use the slider, we can go back in frequency to look at the lower frequencies. There's 16 kilohertz, that was the tone. If we go back further, we can see some frequencies where the shape of the sound source illustrates the shape of the drone with its 4 arms. If we wanted to, we could save that stack as a TIFF sequence of images that could be input into MATLAB. But instead of doing that, let's look at the component spectra for the rotors. To make component spectra, we use the Partition ROIs and create an ROI for the first rotor and then the second rotor, and so on. And when we have all our ROIs, we can turn on partition mode and then do another frequency sweep. Frequency sweep in this case looks a little different because the beamforming is only being done inside the ROIs. When it's complete, we see the spectra of the array median again, and below that we see the component spectra. Rotor number 1 appears to have a peak at about 5 kilohertz. Rotor number 2 has a peak at a slightly higher frequency, and the other rotors have peaks at different frequencies. The sources made by the different rotors are different because they're spinning at different speeds. That's related to the drone's maneuvering. There's a lot more we could do, but so far we've seen how to process a recorded file, how to make images of the sound source distribution at different frequencies, and how to create component spectra. Thanks for watching. For more information, check out www.optinav.com.